Whoa.
Okay, we should be going.
I think we're going. Well, doggone, guys. Ronnie Heron is my name. Good morning on a Monday. I like to call this program Aging Astronomers Are Us. A special vlog on Monday mornings, 11 to noon. We've done 3.5 years worth already. We call it the SBAU Astro Hour on behalf of the Santa Barbara Astronomical Unit. Yep, Santa Barbara, California's long time, soon to be 70 years old, Astrophysics Telescope Club, based at the Santa Barbara Museum of Natural History, up behind the museum, or it is the museum up behind the mission, which is sort of a museum. SBA holds our first Friday of the month general meetings at 7:30, right after a freebie half hour in the planetarium at the museum. And our very popular outdoor star parties are the second Saturday, a dark night, hopefully, next to the Palmer Observatory. And let's do it. Doggone, we're going to talk this week about the roundup of planets, nail them where they are in the sky, of the two main types of star clusters. We'll focus on some big ones, the Hyades and 47 Tucanae. On a smaller scale, ladies and gentlemen, we will trace down a 140-mile diameter rock in the main belt asteroids called Fortuna. I used to live not far from a town in Northern California called Fortuna.
Oh, that's right.
Yeah, darker skies ahead. Last quarter moon is on Friday. Got to get into some heavy math as applied to physics with a look at singularities, assuming you can look at them. Tim Crawford and I will be buckling up our safety belts and hanging on for dear life for that.
Yep.
Plus a little recap included in that of Jennifer Ito's talk back on Friday the 1st. What's a Penrose diagram? Does the horizon have an anti-horizon? Are you kidding me? Last but not least, a failed supernova. We also have President Jerry's forwarded silly science cartoons, but let me introduce you to Jerry Wilson, probably going to be reelected. We'll see next month. Our president, 7 years, Jerry, captaining skipper of the good starship SBAU. He's married to Pat Forgy. Also married to a Pat, but her last name is McPartland, is Chuck in front of the Ukrainian flag. Don't know how much longer you'll be able to keep that up there now that we got a new administration, my friend.
Yeah, scary.
Outreach, and I'm telling you, incredible outreach. Tom Whittemore has joined us.
Morning.
Editor of our monthly newsletter, former science instructor out at Westmont College, at his own lab, married to Maureen. And son of a gun, there's Tim Crawford, resident lens and telescope guy, expert, longtime SBAU member, who cannot get your questions and comments on the screen through YouTube. I'm sorry. Check it out. What?
Too old of a computer.
Well, no, it's just there's always something. AI loves to play with us. Every week it's something different. I'm amazed we're all on the screen and not at jury duty at the cattle call, like one of the gentlemen. Okay, Jerry, you only sent 3 sillies. One of them was a thought provoker, but you'll probably add more. I sent you one. Did you get the one at McDonald's counter? I just
No.
said it. It's hysterical, but it's too late now. Maybe next week.
Okay.
I'll send it to the rest of you.
No, I only have 4 here total.
Okay, well, I got 3 from you, so
Yeah.
one of them we'll just have to make do. Are we going up for the new lines in
was
space?
a repeat.
Oh,
Yeah,
this is the thought
repeat.
provoker. Yeah, I think we had something like this before.
Yeah.
Whenever a child learns critical thinking, somewhere a conspiracy theory dies.
Yeah, this might be a repeet.
Yeah.
Might
Think it
wanna
is.
send that- might want to send that to QAnon.
QAnon.
Are they still on? Is that still a website? Well, this one I didn't get. Can you expand it? Because I'm not familiar with it. Can you make it larger? 2 gentlemen are talking. Is that a computer, a laptop in front of one of them? All right. The one guy says, I don't think you even know what a hard drive is. And the other gentleman says, I've driven across country with my wife, 3 kids, and a dog. I know what a hard drive is. Da, 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 da. Okay, that's not bad, but I didn't get it. These are the new lines in space, ladies and gentlemen. Constellations, stars moving, and they change, and you go from
Well, this
100
is because of Orion today. There's Betelgeuse right there.
Mhm.
And then after midnight, Betelgeuse is gone, and these stars move slightly. So the author is suggesting new lines for Orion based on the new star pattern, and it would represent a Tyrannosaurus.
Oh, I put down a bird or a rearing horse,
Well, these Tyrannosaurus is a bird.
sort of. But Betelgeuse is the biggest of the dots on the left side. How does that go away, but none of the rest of them do?
It's going to blow up in a supernova.
Yeah.
Oh, is that what you're saying? It's going to blow up?
Yeah.
Well, you know, cosmic things take time, gentlemen, and it may not be in our lifetime, but it probably happened hundreds of years ago and it just hasn't reached us yet.
Mm.
Okay.
Good.
Should be one more. This would
Yeah.
be Schrodinger's ketchup.
Wait a second.
Here it's coming. Schrodinger not only had a cat, but he had catsup. Two spellings on ketchup, C-A-T-S-U-P or K-E-T-C-H.
Yep.
Okay, we don't have it.
It's
Okay, wait a sec.
It's a Sanskrit word, Ron.
Nothing in the bottle. Oh, it's Sanskrit, is that right?
Yeah, Sanskrit.
There it is. Can you? Ah, geez, this must be the slowest damn condiment ever. He says, "Is there any of this blankety blank bottle, anything in it or not?"
The big question.
That becomes an extra item on your talking points. What the hell does that mean? There's a cat in there?
No, Schrodinger's cat, is it dead or is it alive? And in this case, is there ketchup or not?
Yeah.
Oh, okay. So what do it's alive. It's dead. There's no cat. Never mind. It's on the wall in the Oval Office during January 6th. It's where the president back then threw it. Okay, gentlemen, let's talk. Our favorite subject. Ooh, the night sky. Here we go.
Okay, this is the sky in the early evening in the west.
Mhm.
You
Yeah, you got Mercury hidden behind that little house.
yeah,
Mercury was naked,
right down there.
but Mercury was naked eye on Saturday here.
Yeah.
Mhm.
So there's Mercury and Venus. Venus is now taking the lead here. Mercury is just up. Now this is 5 o'clock. So it's not completely dark at 5, but it's dark enough to see the planets.
Really? The inner planets, for sure.
Yeah, these two near the sun, they're just coming out from the other side of the sun, from behind the sun.
And still no T Corona Borealis.
No.
Okay.
So those planets will never be in the eastern sky or the west behind us, the eastern sky.
Yeah, they were in the eastern sky up till about a month ago.
Mhm.
Okay, how? If the sun's in the west.
They were on the, if you look at the sun, they were on the right-hand side, which is our east, and they were going around, got to get on the screen here. They were going around the sun. And,
Ron, we're referring to the morning sky when we say that.
yeah.
Mhm.
Yeah, that was a month or so, several months ago, they were in the morning sky,
Mhm.
and they were headed to go behind the sun.
Really? But they were in the opposite direction?
Now they've gone around behind the sun.
Ron, they weren't in the opposite direction from the sun. They were in the morning sky in the same direction the sun was. That's when they were.
Oh, I see. Of course, that's where the sun comes
Yeah.
up. I gotcha. All right. It takes a while for me and Tim to catch up with you guys.
Mm-hmm.
Look at
Well,
it this way. When your dog runs around a tree, when it's going to go behind the tree, you see its butt. When it's coming around the tree, you see its head. Now we're looking at the head.
But now the gas giants can be anywhere, can't they?
They can go around, they can be on the other side of the sun too,
Yeah, well, right.
but they never are in transit.
Okay. Venus does a transit every so often, right?
125 years.
Yeah.
Is that what
It's
it is?
weird. Yeah, it's like 2 8 years apart and then some
Yes.
20-something year gap and then 120-year gap.
Yeah.
Right. The last one was 2012, I think. We
Yeah.
we watched it.
Yes, that's right.
Yeah.
But you
Otherwise,
couldn't
our
see it from here.
otherwise our orbits are so irregular. It's always above or below, and very rarely on the same ecliptic.
No, they're tilted. They're not irregular. They're very regular.
They're just tilted relative to the plane of our orbit around the sun.
Yeah.
Okay.
Yeah, Mercury transits more often than Venus.
Yeah.
Okay. What are we looking at other than okay, let's
Uh-oh.
Jupiter?
Really washed out.
It's washed
Okay.
out, Jerry.
Yep.
Washed out Jupiter.
I
Okay.
mean, these are fantastic images of Jupiter.
Yeah.
So.
Yeah.
Something that big turns a complete revolution in 10 hours. I just can't get over that. I mean, it's booking. That gas is moving.
Mm.
Okay.
There we go.
Wow.
How did you do that?
I switched from Photoshop to Microsoft Office.
Okay.
Well, wouldn't have been able to do that.
So this is, I could probably get this out of Photoshop, but it would take a lot of tinkering with a lot of menus. So this is, these are taken by Christopher Go, who's one of the top amateur photographers, in my view.
Hmm.
And these are apparently the red spot is shrinking, not between these two photos, but it's shrinking from what it's been years ago. I think it's been visible in one form or another for 300 years.
Yeah.
And it's been much bigger and much brighter than this. When I looked at it for the first time about 1960, it was much bigger and much redder than this. It wasn't nearly the same color as this. It was a lot redder.
And a couple of years ago, it was the great flesh-colored spot. It was really pale.
Yeah.
Huh. Do
Well,
they know how?
I came to a talk at UCSB once from a guy up at Berkeley who studies planetary atmospheres, and he was predicting that the Great Red Spot was going to go away in the next 50 years, and that was 20 years ago. So,
30 to go.
yeah.
I'll be watching.
Well, I've heard that it's 3 times the size of Earth and 2 times the size of Earth, and lately it's the
No,
size of.
it's about 3 times Earth right now.
Do they know how fast the gas is moving? Which
Yeah.
would be
Yes.
wind. Huh?
Yeah, it's like 300 miles an hour at least.
Yeah.
300? It's Uranus or Neptune that really has the fast gas, don't they?
1,200 miles an hour. Yeah, Neptune.
Wow.
Yeah, someday people are going to be windsurfing on Neptune.
Yeah.
It's going to be dramatic.
Supersonic windsurfing.
Yeah.
But all those layers, those strata go at different speeds around it, don't they?
Yes.
Sort of like the sun.
Yes.
Oh.
It's a fluid.
Hmm.
Okay, but
At least
does
what we
it never
see.
does the sun twists itself up by doing that? Does that same effect happen
No,
on?
the sun it has fusion going on in the middle. So it has so much heat that it is ripping the atoms apart. So you have a lot of ions, and moving ions create a magnetic field. Jupiter does not have a lot of ions. It's got a lot of atoms. So there is a very strong magnetic field, but it's nothing like the sun's.
And it doesn't get twisted up, but it's very weird. It has multiple poles.
Yes.
Huh.
Ours actually has multiple poles too. It's not a single field. And some of the field lines in some places in the Earth, the magnetic pole has reversed locally.
Can I use this moment to tell you guys something I read in the Times? This was a headline on Tuesday, November 12th. New York Times said this: much of our understanding of the planet Uranus comes from a single flyby nearly 40 years ago. I assume that was Voyager. But they go on to say, but the planet may have been having a freak event just as the space probe passed. You guys know what that is? What that's all about?
That was another magnetic field thing.
Oh. Okay, well, all I got was the headline, but
Yeah.
I would imagine they go through those things all the time.
Well, there's speculation that Jupiter in particular may have superconducting crystalline hydrogen in its core at the extreme pressure, and that would create a magnetic field.
Well, yeah, the Juno probe has found that it's got a much larger core than they thought. They used to think it had an Earth-sized nickel iron and silicate
possible
core,
rocky core.
and then the metallic hydrogen around that. But now they think that the metallic hydrogen core is much, much larger and has the nickel and silicates in solution, like they're dissolved in it. And so that's why the magnetic field is so intense and so weird.
But all the metallic elements on the periodic table can generate magnetism, but to be magnetized as hydrogen, you got to be compressed.
Before it will conduct electricity, yes.
Yeah.
And you suppose that's true of all the gases? Your nitrogen, your
I
oxygen,
don't
compressed
know
in
enough chemistry.
No, if you compress gases, they generally don't become magnetic. If you compress them, they become conductive or
Yeah.
superconductive. And once you do that, then you can shake the thing or rotate it, and you can get the electrons to mechanically move differently than the cores, the crystalline atomic sites. And that constitutes a current, and it's the current that generates the magnetic field.
Huh.
Well, I've heard water when it gets compressed down beyond that ice, even thicker or heavier than ice, it gets weird. It's a totally different type of ice.
Well, there's a crystalline form of ice way down that is stronger than steel. You can actually use it as a structural element if you can keep the temperature low like that. And they had this great science fiction book I read back in the 50s or 60s where they had Ice Nine,
It's,
Cat's Cradle, I think it was called.
it's
Oh,
Vonnegut.
cradle.
That's, yeah,
What's
Ice
that?
Nine that was Kurt Vonnegut. That's
Yeah,
from,
that's right.
There was actually a secret proposal in World War II called Project Habakkuk by the British to make an aircraft carrier
Oh,
out of
yeah.
ice.
Out of ice mixed with sawdust.
Sawdust. Yeah.
Pykrete, it's called.
Yeah.
Geez, what would happen if it got hit by a 12-inch shell? My God.
Well, it was
Not much.
fairly tough stuff.
Yeah.
Well, what would happen if they go to the down to the tropics?
Yeah. Sail fast.
Are we visiting
Okay.
an there?
This the problem with going to a different way of displaying these images is that the better picture doesn't represent, or it doesn't keep track of the order I put the things in.
Yeah.
So can you see this, or is it too washed out?
It's
It's
very
washed-
washed out.
washed out.
Oh, bummer. Okay. Hang
Well,
on.
there's not a lot to Saturn. It's pretty white, isn't it?
Why
No,
don't
it's
you
kind of
just-
yellowish, but yeah.
Yeah.
You could scroll through your Word document that you email out.
I'm not sure that would do it, but we'll give that a try. This should be better.
Yep.
It's better,
Okay.
yes.
Mhm.
So here, this is also from Christopher Go.
Hmm.
It says the dark dot near the lower left limb there is the shadow of Rhea,
Hmm.
the second largest moon. Rhea itself is the white dot down here. And this one over here is Tethys.
Mhm.
Cassini, of course, gave us lovely pictures of those moons, I'm
Mhm.
sure.
And you can see this, the Cassini gap or ring or whatever it is, gap.
Cassini
Mhm.
division. Yeah.
Division.
Yeah, thank you. And then there's a faint ring in here.
The crepe ring.
Yeah. And there's a lot of structure. There's in our size telescopes, I think you can see about, if you get lucky in the seeing, you can see about 4 rings. But there are many more subdivided rings.
Christopher Go, by the way, is from Cebu in the Philippines, that island, and that's where Edgar's from.
Oh, I didn't know that. Okay.
Huh.
Okay, just a quick flip of the wrist here.
Oh, Pleiades.
Now,
That's how they looked last night in my binoculars, Chuck.
oh, could you see the nebula?
Not in the binoculars, but I've seen it in scopes before. Yeah.
Now, the point of this part of the talk is that there are 2 major and 1 minor subdivisions of star clusters here. There's open clusters, of which this is one of the largest and easily visible. There's 3 or 4 that are visible to the naked eye. Omega Centauri is the third. It's the third brightest, but I didn't take a picture of it. Wikipedia and other sources are very confusing on this topic. If you look up what's the largest star clusters visible, it gives you the size of them irrespective of their distance. And what I would like to have a list of is the ones that show the largest angular diameter in our sky, but there's no such list, so you have to look through and fumble.
Visual appearance, yeah.
Yeah, so this one is
Probably Coma Berenices,
Mhm.
the cluster there is probably the biggest, Milot, whatever, 111.
yes,
Yeah.
I think that is correct. But I wanted to show the ones that you see at night that are the biggest or the brightest. And so there are three types of clusters. Two that we normally talk about, the open cluster and the globular cluster. And we'll have a couple of examples of each. And then there's the embedded cluster, which is usually an open star cluster that is embedded in a nebula. And the best example of that is the trapezium in the Great Nebula in Orion, which you can't see it very well because it's embedded in the nebula and it's actually a star-forming region. And the nebula's, the star cluster's members are actually being created. They're being birthed in there. So you don't see these real well, but they're really good X-ray pictures and radio wave pictures of these embedded star clusters, but we're not going to get into that this time. This one could look like an embedded cluster, but I believe that the nebula you see around this is not associated with the star clusters. It's sort of in the way of it. The star cluster is passing behind it.
Right.
Colliding with it, yeah.
Yeah.
Right.
Well,
And the
would
fact that it's blue, tell you it's reflection.
Right.
Yeah.
It's
Dust.
not activated. If it were red, it would be excited
there would
by
be-
the light. Yeah.
Then it would be
it
an
would
active
emitted.
part. Mhm.
Right. So the Pleiades is one of them. And this one is easy to spot. It's really relatively small on the order of things. This one, the Hyades, is not easy to pick out or display. It's really their strongest naked eye visibility. I keep looking at Taurus and there's kind of like this faint patch that I see there. And when you look at it with binoculars, you see the stars, the bright stars in this picture. It's this region of the
Mhm.
Taurus. This is the head of Taurus, the bull, and these are its two horns going up. But when you look at it in a star chart like this, it adds so many other stars that the Hyades is actually obscured. But it's these stars here, and it's very scattered. It's very big, but it is a star cluster. And in order to be an open star cluster, they have to be gravitationally bound to each other.
Yeah.
And they're separating.
You see that fuzzy patch out to the left? That's a really beautiful NGC object. I can't remember the number of it, but it's really pretty in a small refractor.
And the Hyades look so sparse because they're like the closest open cluster.
Yes.
That's right. It's probably the most studied star
And one of the
cluster.
most difficult to take a picture of with a telescope. You need just basically your camera. So these very popular C-star things that are coming out now with their little teeny lenses and very wide field of view is a perfect item to show the Hyades and the Pleiades in. I've taken a picture of the Pleiades many times, but I have to paste everything together to get a full picture of it.
Yeah, and again, I consider the Hyades and the Pleiades just wonderful binocular objects. Beautiful.
Now this is this is from my planetarium program, the Sky 6. This is an actual photograph
Okay.
of it. And you really don't pick it out. It's this region.
Yeah.
They're roughly aligned with each other. There's a slight rotation difference.
Yeah, there's a couple of beautiful double stars in that group, the Hyades. There's one of them. Okay, and you can actually see that in your planetarium program and
Yeah.
Yeah. If you go back one, bingo.
There.
Right. Yeah, there's a
there.
couple. Yeah, there's two pairs that are really pretty in binoculars.
There's a pair there. Different brightness pair. Yeah.
I'm sorry, gentlemen, I can't see the star cluster there. Well, those
Yeah, I know
names-
it's tricky because it's obscured, but kind of squint, and a lot of the faint stars will go away, and you'll be left with this.
Would part of the definition of a star cluster be they're all orbiting each other?
Not that strong. They're weakly gravitationally bound to each other. And as they evolve, because they started from a nebula where they were tightly bound, not tightly like a globular cluster, but they were closely bound. And then they spread around because they're each in a different orbit around the center of the galaxy, and other stars pass by and star clouds pull them apart.
Well, do
But
the
They
word
gradually evaporate, but they still, even when they're very, very loosely gravitationally bound, they're traveling in the same trajectory. So then they become, from a cluster, they become a moving association,
yes,
like
exactly.
we are with the Big Dip, most of the stars in the Big Dipper.
Right. And that appears to be the where we came from when we were made out of a nebula. Our sun, we were with the Ursa Major Association, but we
But
got kicked out for talking out of turn.
Now,
Yeah.
this is an image here, Jerry, or is that
No, this is an image. This is a photograph,
Yeah.
a wide
So,
field
so
photograph.
Jerry, would that be Aldebaran down there? It looks,
Yeah.
doesn't,
This one,
doesn't
yeah.
look very red. Okay.
Now, this one, you can see a whole bunch of little spikes around it,
Mm-hmm.
more than the James Webb. So, and different proportions. 1, 2, 3, 4. So there's 8 spikes around there.
Mm-hmm.
That's due to the hexagonal aperture, diaphragm in a camera lens. Camera lenses will show a lot of spikes like that, depending on how many blades of the diaphragm it has.
Mm.
now? I'm
Really?
not sure at Westmont what I saw. There was just a few stars in it. Chuck told me it was all washed out.
Yeah, you
Mm.
were seeing this part up above Aldebaran in this image, where there's the two really obvious the two really obvious ones. Yeah, just
Right
that
there.
small section near there. Yeah,
I was right about there, huh? Okay.
yeah.
Yeah,
Well,
because
you saw this, but you didn't see Aldebaran.
no,
That's a very narrow field of view. You're not going to be able to really
Yeah.
appreciate the Hyades.
yeah, I had a little 6-inch and I had a real low power eyepiece, but it
Yeah,
didn't,
not low enough.
not
Yeah.
low enough.
Oh, but just Aldebaran was out of the field.
Just out, yeah.
Mm.
Okay.
well,
Now
is there any
among the-
relation? Is there a relation between the words Pleiades and Hyades?
they're both words.
Well, they're both groups of I think sisters
Yeah.
But are they
in
Greek?
Greek mythology.
Greek.
Okay,
Yeah.
Greek. That's why the DES at the end. Okay.
Yeah.
There's a great story that Chuck tells about the Pleiades, the Iroquois myth.
The
And,
ladies who ate onions. Yeah.
and that kind of is really nice because it involves both the Pleiades and the Hyades.
Yeah.
Okay. Now, this is something that we do not see here, and we will never see. This is, of course, way in the south. This is the Large Magellanic Cloud
Mm.
and the Small Magellanic Cloud. Last week, we had something we looked on in this area in the bridge between the two, the hydrogen bridge. But this is probably the second brightest globular cluster in the sky right here. It's called 47 Tucana, and it is easily a naked eye object. Matter of fact, it pulls your eye toward it because it's brighter than most of the stars around. And it actually looks fuzzy to the naked eye. So, but this is a globular cluster, and it is one of the most heavily populated and nearest to us. This is the core of the 47. And you can count them up here, but there's probably 1 million stars in there. These are red giants, older stars. All the rest of the stuff is hotter stars and much older stars and much less massive stars.
And that's in our galaxy, not in the Small Magellanic.
That's a good question.
They don't know whether it's in our galaxy.
No,
It's
that's
closer to
tricky.
us.
You're asking a good question. At some point, if you map in 3 dimensions where the globular clusters are around our galaxy is like a disk, but the globular clusters occupy the surface of a sphere around us. They don't conform to the disk about the galaxy. They're orbiting the center of the galaxy, but they're orbiting in orbits that are all tilted all over the place. They're not conformed to the disk of the galaxy.
Kind of like Pluto in our solar system.
Yeah, Pluto is tilted
Or like the
slightly, but
Oort
these
cloud.
globular clusters are sometimes up to 90 degrees off.
Didn't
more
realize
like
they were in
Oort cloud.
orbits.
So this
What?
may be outside the ecliptic of the galaxy. Interesting.
Well, ecliptic, Ron, is just the path of our sun that we see in the sky.
Right.
So it's not ecliptic. You mean
Yeah, you
equator.
mean plane of the galaxy.
Yeah.
Plane. Yeah, that's what I meant.
And Tim,
But-
what were you saying?
I said I did not realize that globular clusters had an orbit around the galaxy.
Yes.
Yeah.
Oh, yeah. Oh, yeah.
And
Yeah,
there
you
could
can
be-
see trails, tidal trails coming off of them too that map some of the orbit.
Yeah.
Wow.
So if you ran in, if the Earth passed through with the orbit of a globular cluster, you'd have a meteor shower, but of stars.
Yeah.
And the globulars they actually reside in this globe around the galaxy and in the plane of the galaxy.
They pass through the plane. I don't think anyone has complete conformity to the plane.
Okay.
Well, this is
But
something
I could
we
be wrong on that. So, ladies and gentlemen, phone in.
Yeah.
But the Milky Way captured this probably from
No.
what?
No, these are more like things that formed at the same time the Milky Way was forming. And the core of our galaxy was the biggest one of them. And so it got most of the star-making material.
Most of these things start as big spheres or big lumps, like Chuck is saying. And through gravitational interactions and collisions, but not actual smack into each other collisions, but through close gravitational attraction, they average out their angular momentum. And things that are round and rotating generally become flat and rotating. The globular clusters did not conform to that gravitational collision scenario, and they kept their own orbits.
God.
And they're round, not flat, right?
Right.
Yeah.
They're elliptical. Ellipsoidal.
I used to think, scattered little single stars outside of the plane of the galaxy, but millions of them in a
Yeah.
ball.
Yeah.
God.
I think M13 is also approaching 1 million.
Yeah.
There's speculation there.
No, I think that they actually have methods of estimating it. They can't photograph each one, but they have estimates of ways of estimating it.
Based on the mass and the motions within the cluster.
Right.
I always tell people that ask the questions that they paid some guy minimum wage to count them,
Yeah.
and that the first night was okay.
They do, and it's called a graduate student.
Yeah. So another comment that I always get is that do they get more dense as you go into the center? And I said yes.
Mhm.
So but they always they ask again, do they ever touch? I said I don't think so.
No.
Yeah, they do. You get what are called blue stragglers, where some of them have collided with each other and they're more massive and younger looking than they should be.
But this ball
And they actually evaporate. They will toss members out and lose members in these tidal trails, but they actually get denser because each time they toss one out, it's like two of them have gotten closer in the interior. And so even though they gradually lose stars, they do get denser.
And the distance between these stars as they get towards the middle, they get more and more dense.
That's
all these
right.
distances they get closer, but I was never able to answer just an average distance to these stars kind of on the outside.
I think it's like light weeks when you're way close in the interior there.
Okay.
You suppose there's a black
Now
hole?
this is 47 Tucana, which is listed on the internet sources I looked at as the second brightest globular cluster. The brightest is Omega Centauri, which is also a southern.
Yeah, we can see it here. We can see it here.
Barely.
What's our distance on this, Jerry?
What?
What is the distance on this one?
It'd be
I think
tens of
it's-
thousands.
Tens of thousands of light years. You suppose science thinks there's a black hole in the center of most star clusters?
There's
It
a
is
couple
on
of
some of
globulars
them.
that they've found black holes in, but I wouldn't say star clusters, maybe in globulars.
Which this is?
Yep.
Yes.
Mhm.
And it happens to be right next to the Small Magellanic Cloud.
Yeah, that's just a
No, it
perspective.
doesn't give a distance for that. I'd have to look it up.
Okay, I'm going to look it up too.
Okay.
It'll be tens of thousands. It's between us and the Magellanic Clouds.
Yeah. Okay.
Okay.
Now we're going to do some star hopping here. We're going to look for an asteroid Fortuna, 19 Fortuna, which is another one that is on the large size. It's actually almost round like Ceres is, but it's smaller than Ceres. So it's round-ish.
So it's not a dwarf planet.
No, Ceres is a dwarf planet. I
Yeah,
don't know.
the definitions they came up with are a little bit lame. They'll
Yeah.
improve that, but
Maybe.
it's not gravitationally dominant the way Ceres would be.
Okay.
I thought it was odd in the description that came in the write-up that it said it's very similar to Ceres, but then they say it has a very dark surface, and Ceres definitely does not have a dark surface.
Yeah. I mentally stumbled at that point too. So anyway, this is located near Zeta Pisces. This is the constellation Pisces. And this is Zeta right here. For those of you with a Greek alphabet background, that's Zeta.
Mhm.
My planetarium software doesn't show these kind of labels. So I have to go to some other thing to get the Greek labels.
Mhm.
The idea of these Greek labels is that you start at the beginning of the alphabet with the brightest star, or sometimes the second brightest star, and then you go through the rest of the stars. It's only approximately follows. I think it was assigned by someone who got tired of doing it.
But where is Fortuna?
Fortuna is
Off the screen.
no, it's
Oh.
right in there. See, this is Zeta here, and this is Epsilon. So you can see that on the line between Zeta and Epsilon, we're about 1 to 1.5 tenths of that.
Well, now we're more down by the curl in it. But Zeta is pretty much almost in the middle of this image.
Yeah,
there
this
they
one
are.
here. See, there's Zeta and there's Epsilon. So it's right, yeah, it's near the curl of Zeta right there.
Well, no, it's near the curl in the orbit because we're already at the 15th. We're
Oh,
past.
yes, that's right.
Yeah.
We are at the 18th here, so 15, 16. We're down here, yes. Oh, yeah, the line, yeah. I was just doing the line. I was going to do the line next. You jumped ahead of me. So anyway, it's down here. I guess we could make a triangle, a flat triangle.
Yeah.
It's
So
whipping around.
there, so it's right around there.
It's
Right
gone.
on the ecliptic. What a coincidence.
Yeah.
Huh.
And Ron, what's happening is we're passing it in our inner orbit, and so that's why it looks like it's backing up.
Yeah, it's retrograding.
That's retrograde. Okay. But otherwise it's in the belt, right?
Yes.
Within the asteroid belt between Mars and Jupiter.
Yeah.
And this is a Hubble photograph of it. In reading the details, this is about 2 or 3 pixels. So you can actually see where the pixels are trying to approximate, the processing is trying to approximate a shape from the square pixels. So this is as close as we get to an actual picture of it. Hubble didn't get very close. So, or this was not Hubble, but there was
Webb?
like the name escapes me of the satellite.
Oh. It's a large.
Galileo or Cassini going by.
No, not Cassini. It was something with an E in it. And I think it was a European satellite. But anyway, enough of that. Whoops. Now, there are a bunch of nuts that go out at all hours of the night and set up at estimated positions so they can observe the transit of these objects against background stars. And from the length of the disappearance of the star and where the person is on Earth, they can estimate the perimeter shape along with those photographs. And then they also have available to them brightness maps as the thing slowly rotates. And putting all those things together, you can get a good feeling for the shape of the object. And this is Chuck does this as a hobby, and it's quite interesting. I've looked up things to see if I want to do that, but it's very disrespectful of my sleeping patterns.
Yeah, boy, he's out at all hours.
I was out night before last up in Figueroa Mountain Road, freezing my butt off trying to get one, but it was 21 degrees from the moon, and the moon was nice and full, and it was a
Yeah.
magnitude 13 star. But pulled it out. It wasn't a positive, but I did get the star and get enough signal to noise to see that it was negative.
Okay.
Hmm.
So is that the one where they moved the estimated line on you by 7 miles?
No, that was a previous one at Gaviota. Yeah.
Oh,
This one was only like a 2.6 kilometer diameter asteroid, and I was about 6/10 of a kilometer from the center line. So it deviated a little from the predicted center line, but it was small enough that that meant I missed it.
it slipped through.
Yeah.
Okay, so this is the path of the shadow that the asteroid would make on the Earth for that one that we just showed the occultation pattern for.
It's really washed out, but it's
Yeah.
going over like Vancouver.
Oh, sorry. Let's get to
Not washed out on your screen, Jerry?
what's that?
Just our screens wash it out. Yours is fine.
No, it's the display interaction with Zoom.
But what do you see? You see the washed out version or the
No,
cleared
I
up?
see it. I see it fine on here.
Hmm.
But we don't. That's interesting. Okay. We're switching over, I assume.
Yep, that's it.
Oh yeah, there we go.
Okay. So this is the shadow, the predicted shadow from the orbit they know or the orbit they think it's in. And so they alert people that are in or near this line that participate in the program, and they go out and set it up and they spot the thing and measure the time, the duration of the disappearance of the occulted star. We're down here near Point Conception under the path of Vandenberg Space Force Base. By the way,
And
one
what's
went up last night.
what's really nice is that 120-degree line of longitude passes almost right through like Refugio. So that makes it easy to tell from a quick glance at the map whether I'm going to have a shot at it.
Uh-huh.
Well, I'm
Okay.
sorry I missed what it's occulting.
It's occulting a star. In this case, Tycho 57801169-1.
Okay, but without that occultation, you could see the asteroid by itself.
No.
You could for this one. This one's big enough and bright enough that you probably could.
Oh, I thought it was dark.
Well, dark surface, but
Okay.
still, to have a number like that, what was it, 19?
Yeah.
That's a pretty bright asteroid.
Yeah. Okay. Yeah, I don't see the star listed here. It's a little fuzzy, but
So if
Those
you
are
were
the
to,
names of all the people who observed it.
oh, by color code.
Yeah.
well, since you're not in that line to the north of us, Chuck, if you zeroed in, you'd see the star go right across the top of it or below it, right?
Yeah.
Right, yeah. It might even look like it fuses into one, but it wouldn't block out the star.
Well, that'd be worth watching.
And in this case, actually, the asteroid was brighter than the star. If you look at that previous one, the star was really dim and the asteroid was brighter. And that's why the drop is so small here, because it's blocking only the starlight, and that was contributing less to the total.
Yeah, here's the total light of the two. Here's the light of just the asteroid. And here's the light of the two again. So this is a very clean measurement of time.
Yeah.
So that's the occultation in the middle, the dip.
Yeah.
Yes. And you can see there's always noise from scintillation in the atmosphere and stuff like that.
Yes, and this noise is real noise.
But what do all those dots represent?
Every
Brightness
dot is one data point.
It's not
Each one of those is a measurement of the brightness of the star at that instant.
Right. But
Is that the noise?
The squiggle in it is the noise, yeah.
yeah,
I mean, no, the dots. They're
the
not
fluctuations.
Yeah. The dots are measurements and there's noise on the measurements. So you see
Yeah,
the
each dot is not a separate person.
It's a separate frame of the camera, basically. It's like
Right.
depending on their frame rate, it could be 1/30th of a second.
And
So
some
those
of
are
these you
multiple
see,
fast measurements of the brightness.
and some of
think what
these
I'm
you see at the
confused is
same
Gary
time,
was
they're
saying-
multiple measurements, and those are from different people.
Well, this is just a graph from one person here.
Oh, is it one person?
Yeah, they don't combine the light curves. Just because people often have such different sensitivities on their cameras.
Okay. Okay.
So where I was confused is when you were saying there was real noise, and I didn't.
Well, that's the jumping up and down all here is real noise.
Okay. Okay.
So this is your signal size right there. And this is the average RMS value of all these fluctuations is your noise. And so it looks like the signal to noise is about 1 or 2.
Oh,
Yeah, and some of that depends on the scale of the brightness over here, but yeah.
There's a lot of things, yeah.
Yeah.
But the key thing is that this noise is time dependent, and that makes it real noise. Spatial noise is not real noise, it's a pattern noise. It looks like noise, but it's not noise. Now, what do we got here?
are we going to singularities, are us, for Tim and I and math? You got less than 15 minutes to convince us, Mr. Prez.
I'm back in the thing that doesn't respect my, oh yeah, this is good. Yeah, this is getting back to
Planetary.
this coming Friday, the last quarter moon, and then we'll get into darker skies. This is 11th magnitude IC 2149 near Menkelin.
In the
This is a small planetary nebula described visually by Stephen James O'Meara. Has an apparent magnitude of 10.6 and 12 arc seconds across. And it's located in this region of
Auriga.
Auriga. So, okay, and
Can I mention something really quick here? The
Go
other
ahead.
night we were looking at Auriga, and Chuck and I were mentioning the 3 clusters, the 36, 37, 38.
Mm-hmm.
And I think it's, Chuck, it's 36 and 38 that are inside the border of Auriga, and 37 is the one that falls outside.
yeah,
Yes.
I think
but that's if you draw, and I do that too. I
Yeah.
don't like this stick figure. I draw a line here in my mind and then up here.
Yeah, we were trying to remember which one was outside, and
Yeah, 37 is outside.
Yeah, 37. Okay, well, there it
So
is.
these are all open clusters.
Yes,
They're very nice pictures. They're good. They're good photo shoots.
we might have been able to get those the other night, but I didn't get to them.
Mhm.
The moon was giving me a little tan.
Yeah. Yeah, we were pretty much concentrating on Saturn, Jupiter, and the moon. Although, like Chuck Watson had his sea star and he was doing the Andromeda galaxy.
Alberio was real nice. It was it was very nice.
And the reason we're looking at this is because it's going to be a dark sky Friday.
Yes, and so we can start looking at fainter objects, faint fuzzies, which I much prefer to the planets and the moon.
Sure.
I got satiated on the planets of the moon probably in the 70s. I mean, they're interesting stuff, but who knows?
Well, are you going to be able to talk about the Penrose diagram before
I
we
don't
get?
know if we're going to get to that or not.
Okay.
But anyway, this is the planetary nebula you're looking for. And
Well,
ironically, it's described by Stephen James O'Meara and all the visual observers as being obviously blue. You can actually see blue color. And of course, it's red here, but this is false color, as all photos are. And this is because it's taken in the infrared. This is an infrared view of it.
huh.
Definitely got red.
So, but apparently visually, it looks blue, between blue and gray.
Am I seeing like a little bit of a bipolar there going, left and right?
Yes. It looks like a jet.
Yeah.
And
Well,
then
you
you've got the equatorial stuff going at 90 degrees to that.
Yeah. Yeah. Right there. Yeah.
Yeah. So anyway, that's a nice target to look for. Now we had a very nice talk from Jennifer Ito at Westmont College. She's collaborating with what is it, UC Berkeley and Stanford. And as you all heard of the Big Bang Theory, and the Big Bang Theory, you look at the night sky photographically, and you take pictures of it, and you look back in time, identifying what things are farther away, and everything's moving away from each other. But as you get back in time, things are closer together because they've been moving away from each other for all of the history of the universe. And if you take and extrapolate that backwards, it comes to a point if the Big Bang Theory is right. And the Big Bang Theory, we can observe that the Big Bang Theory does explain all this stuff back to here, which is called the initial expansion, or this is inflation, not economic inflation, but in the time period of 10 to the minus 32 seconds, the Big Bang Theory said we went from the size of a quark or fundamental particle, even smaller. The extrapolation says it's a zero volume, but all the mass in the universe is in there. And that's just a very unsettling way to try and visualize it for us human beings.
It's
So
easier if you visualize it as just energy at that point, though.
that's whatever it is, yes.
Yeah.
So the point is that we want, in order to have the Big Bang be a complete theory that we're all have high confidence in it, we have to understand that this thing really happened. The reason that it's being proposed as such a very rapid extension is that when you look at the cosmic microwave background here, there are temperature fluctuations this is an all sky map. These are hotter regions and these are cooler regions. Well, if the thing was if you know thermodynamics, heat flows from hot regions to cold regions. So the fact that these regions are separated from each other is a big deal. And in order to do that, the Big Bang Theory has postulated that there was a period of expansion that was so fast that it froze in fundamental quantum fluctuations of that elementary particle. And that's very unsatisfying to a lot of people. And so ways around that, there's two ways to approach that. You develop a new theory, which is going on right now, or you try and get evidence that shows that this happened. And Jennifer Ito is one of the people that is trying to work on it, that is working on an experiment and building a mechanism that will allow us to measure this, because we can't see past this. This is when the universe, first particles, first nuclei, first light. This is 300,000 years after the Big Bang. And this is the map we see right here. This is the sky 300,000 years after the Big Bang. We can't see past it. This is the fluctuation in the initial fireball that created the universe. So we have no hope of actually seeing back to here, except for the fact that there's such mass back here, or energy, that there may be gravitational wave structures that are embedded on this cosmic microwave background that could only be put there by that kind of inflation. So that's what her experiment is trying to measure this to higher precision. The temperature difference between the dark and the light here is 10 to the -4 Kelvin. That's 1/10,000th of a degree. And the average temperature shown here is 2.75 degrees Kelvin. So it's pretty cold already. So what they do is you take this as a map and you do a Fourier transform of it, which gives you a power spectrum of the distribution of these things. And it will tell you if there are any gravitational waves that resulted from that initial inflation. So she's trying to get experimental proof that initial inflation existed. So there's two places in the universe where we have issues like that. We have what's called singularities. This is one of them, where we have zero radius, but very high mass or energy at the beginning. And also at the core of black holes, we have a singularity, but not observed, just hypothesized, because if you extrapolate from what we can see to the inside of it, it just goes down. You have a ruler and a piece of paper, and you basically go down to a singularity inside the black hole. But we can't see inside the black hole. So people are doing a lot of theoretical evaluation, trying to understand what is going on inside a black hole. And this is a diagram of our universe, but it's been conformally mapped so that this is time and this is space. So this is infinitely far away from where we are now here. And this is infinitely long ago in time, and this is infinitely far in the future. And it's just been simply mapped so that we can handle everything in one diagram. And that's exactly what we have here. This is simply a conformal mapping of the whole sky. So
is that CMB?
Yes.
Okay.
CMB, yeah.
Okay.
So if you take this diagram, cut it out, and allow it to stretch and stuff, you can wrap it around a sphere. And so that covers the whole celestial sphere. It's just that this is a map that distorts it because we want to put it on a flat piece of paper. This conformal map is the same type of thing, but it handles time. Remember we discussed light cones a while ago, future and past, and someone making the journey, traveling up in our four space, where we have this line is 3 spatial dimensions, and this line is time. So we're all just moving up like this.
Commentary, is it kind of coincidental that this singularity kind of matches what Einstein said about approaching the speed of light, mass becoming infinite and time slowing down? And
anytime you get to something becoming infinite, you went off the table. Your ball didn't make it to the hole, it went on the floor. Point is that if you go to infinity, it's because your math had division by 0. And that's an undefined operation. So it's incorrect to say that it goes to infinity. It approaches infinity, but it does not go to infinity. Now, okay. Brian Cox has a very nice explanation for that. And that's some of these things. And as I do it more and more, I understand it better. So, but not well enough. And we're not going to get into these Penrose diagrams because I think they're just confusing. But
Jerry,
but the idea is that Brian Cox said you don't want it, you're thinking of black holes wrong. You don't want to think black holes as a singularity in space inside, even though we regard them as something in space. The point is that space and time are, once you pass the horizon, event horizon, time and space become so mixed up, and that's what this diagram is trying to unravel, that the singularity, if it exists at the center of a black hole, is a moment in time. It's not a point in space. Yeah, that is space. Once you get inside the black hole, space and time are mixed in very counterintuitive ways. So as you fall in, and the best way to think about it is if you fall into the black hole, of course, you can turn around and you can face where you came from, and you can see out, or you can see the light coming from outside and it hits you. And you can see, because the event horizon is not a real thing, it's just a mathematical construct. So you can still see what's going on outside. But if you turn around and look down inside, you always see a black hole. That black hole is shrinking as you get closer to the singularity, but if there is a singularity. And that's a real horizon that you can't pass. So they're breaking it up into false horizons and real horizons. The false horizon is the one you just passed through, which you see back there when you pass through it. It's not there because you can see the whole universe. But from the universe point of view, they can't see you.
Is it kind of like the inflation could have been like a huge black hole that turned itself inside out?
Inside out.
No, I don't think that's the intent. It's space and time are no longer, well, I don't know. I don't completely understand this. No one else does either.
Yeah.
But they're very interesting thinking on this. For a while, what's his name? Just a few more moments. Jim Hartle here at UCSB, who's now deceased. What a loss. And Stephen Hawking were working together on what they call the no boundary proposal. And what they're working out is that there is no boundary. There is no, simply get rid of the need for singularities there. And their theory generated the phrase, what's south of the South Pole? And so if you look at people on the Earth, we are you can imagine that we're in a two-dimensional world, say like Flatland, which is that famous book where you're in a piece of paper. But for a higher dimensionality, the piece of paper is actually now the surface of a sphere. And so you can move around on it, but you never come to an edge. And Hartle and Hawking are trying to do that for our universe, our four-dimensional universe, space-time, making it conformal to a four-dimensional surface that has no edge or no boundaries. And it's a very interesting theory. And I think there's a lot of promise in it.
Wow.
Did I sufficiently confuse everybody?
It was great. It's really a nice discussion, Jerry.
Yeah, Tim and I are going to sleep on that, Jerry.
Yeah.
We'll give you a 3-page report later. Gibberish, but whatever. Let's continue this discussion, gentlemen, in the future shows. We're approaching our 4th year. All right, everybody, thank you. On behalf of my education, join us again next week for program number 196 of the Astro Hour, closing out the month of November. Friday, the 6th of December is our yearly elections month and our in-house members-only science speeches from Dr. Farshad Barman, City College's Sean Kelly. Do tell your friends about us, and thank you very much for educating.